This is the first part of electrical engineering previous year question paper with a detailed solution of Isro-Vssc technical assistant. The exam held on 2016. Advertisement number 291 and post number 1285. Question number 1. Between 200 watt and 860 watt lamps of the same voltage rating, the resistance of 200 watt lamp will be. Answer option A, higher. Power dissipation in a lamp P equal to V square by R. Since both bulbs are rated at the same voltage, so that resistance of each bulb is inversely proportional to its rated power. Therefore, the resistance of 200 watt bulb is greater than the resistance of 800 watt bulb. Question number 2. The energy of a charged condenser is given by C equal to QV by 2. The energy stored in the capacitor E equal to half Q square by C. We know the charge on a capacitor Q equal to CV. Substitute this equation, we get E equal to half CV square. Again substitute that equation, charge on a capacitor Q equal to CV. We get E equal to half QV. Where Q is the charge stored on the capacitor, E is the energy stored in the capacitor, C is the capacitance value, and V is the electrical potential difference. Note: energy stored in condenser. A capacitor is a device which stores energy in the form of charge. The process of charging up a capacitor involves the transferring of electric charges from one plate to another. The work done in charging the capacitor is stored as its electrical potential energy. Question number 3. For a p-pole machine, the relation between electrical and mechanical degree is given by answer option D. Q electrical equal to P by 2 theta electrical equal to P by 2 theta mechanical. One mechanical rotation covers P by 2 electrical cycles. Therefore, theta electrical equal to P by 2 theta mechanical. Question number 4. In DC generator having P number of poles and speed of n rpm, the frequency of magnetic reversals will be. Answer option B, Pn by 120. Frequency of magnetic reversal equal to P by 2 into n by 60, which is equal to Pn by 120. That is frequency of magnetic reversal equal to number of pole pairs into revolutions per second. Question number 5. A DC shunt motor runs at 200 volt supply. If the armature current is 20 ampere and the resistance of the armature is 0.5 ohm, the back EMF developed will be. Answer option C, 190 volt. Back EMF DC shunt motor EB equal to V minus IaRa, where V is the terminal or supply voltage, Ia is the armature current, Ra is the armature resistance. Given V equal to 200 volt, Ia equal to 20 ampere. Therefore, Ra also given 0.5 ohm. Therefore, EB or the back EMF is 200 minus 20 into 0.5 volt. We get EB back EMF equal to 190 volt. Question number 6. Semiconductor have electrical conductivity of the order of ohm centimeter inverse equal to option B 10 raised to minus 3. The range of electrical conductivity for semiconductor is 10 raised to minus 6 to 10 raised to 4 ohm centimeter inverse. Electrical conductivity of semiconductors increase with a rise in temperature as more electrons can jump to the conduction band. Additional points: the range of electrical conductivity of for conductors is 10 raised to 4 to 10 raised to 7 ohm centimeter inverse. The range of electrical conductivity for insulator is less than 10 raised to minus 10 ohm centimeter inverse. Question number 7. A 3-phase 3-element meter of 415 volt 50 Hz has its pressure coil rated for. Answer is option C, 415 volt. A pressure coil is rated at a line voltage, that is VRY, VBR, etc. So that pressure coil of 415 volt 50 Hz 3-phase 3-element energy meter is rated at 415 volt. Question number 8. The RMS value of AC is equal to. Answer is option B, 0.707 of maximum value. The root mean square current or voltage or RMS of an AC circuit is the effective current or voltage of that circuit. The maximum value of the potential in an circuit is called the peak value of the voltage. The average value of the potential and current of an AC circuit for a cycle is called average potential and average current. Average current over half cycle, that is I average equal to 2I by pi. Average current over complete cycle equal to 0. RMS current or IRMS equal to I by root 2, where I is the maximum or peak current in the circuit. So RMS value of AC is equal to 0.707 of maximum value. Question number 9. The total number of coils per phase per coil is, answer option B, total number of coils divided by number of phases into number of poles. Detailed description is, the total number of coils per phase per pole equal to total number of coils divided by number of phases into number of poles. Slots per phase per pole equal to number of slots divided by number of phases into number of poles. The number of slots per pole per phase determines how the winding layout is arranged. It is also disclosing information about the winding factor and its harmonics. If the number of slots or poles per phase is an integer, the winding is called integer slot winding. If the number of slots per phase per pole per phase is fractional and is superior to 1, the winding is called fractional slot winding. If the number of slots per pole per phase is fractional and inferior to 1, the winding is called concentrated winding. Winding with the same number of slots per pole per phase have the same winding factor. They are winding layouts of the same basic sequence repeated by the number of winding symmetries or machine periodicity. Question number 10. A lap wound DC machine has 400 conductors and 8 poles. The voltage induced per conductor is 2 volt. The machine generates a voltage of, answer option A, 100 volt. In a DC machine, induced EMF E equal to voltage across each parallel path in a lap wound DC machine. Here number of parallel path A equal to number of poles P. Given number of conductors Z equal to 400, number of poles P equal to 8, voltage induced per conductor is 2 volt. We know that a number of parallel path A equal to number of poles P in lap winding. Therefore, number of parallel path A equal to P equal to 8. Now, number of conductors in each parallel path equal to 400 divided by 8, which is equal to 50. So, EMF induced by machine E equal to 50 into 2, which is equal to 100 volt. Question number 11. A Kaplan turbine is, answer is option D, low head axial flow turbine. If the water flows parallel to the axis of rotation of the shaft, the turbine is known as axial flow turbine. For the axial flow reaction turbine, the shaft of the turbine is vertical. The lower end of the shaft is made larger, which is known as hub or boss. When the vanes on the hub are adjustable, then the turbine is known as the Kaplan turbine, and when the vanes are fixed to the hub, then the turbine is known as propeller turbine. Kaplan turbine is a low head axial flow turbine with adjustable vane. This is the classification of turbines. Flow, energy, head, specific speed and example. Tangential flow, energy is impulse and head is high head, 300 meter and above. Specific speed low on 0 to 60 rpm. Example, Pelton wheel turbine. Radial reaction energy, head is medium, 30 meter to 300 meter. Specific speed medium, 60 to 300 rpm. Francis turbine. Axial reaction energy, head low, less than 30 meters. Specific speed higher, 300 to 600 rpm. Propeller turbine, 600 to 1000 rpm. Kaplan turbine. Question number 12. The insulation resistance of a cable of length 10 km is 1 megaohm, and for a length of 100 kilo ohm of the same cable, the insulation resistance will be, answer is option C, 0.1 megaohm. Insulation resistance of a cable R equal to rho by 2 pi L log R, capital R by small letter r. Insulation resistance is inversely proportional to length, that is R1 by R2 equal to L2 by L1. Therefore, R2 equal to R1 into L1 by L2. Therefore, which is equal to 1 mega ohm into 10 by 100, which is equal to 0.1 mega ohm. Question number 13. An RLC series circuit remains predominantly inductive. Answer is option C, above resonant frequency. In a series RLC circuit, the net impedance Z equal to R plus J XL minus XC, where XL is the inductive reactance which is equal to omega L and XC is the capacitive reactance 1 by omega C. So that the inductive reactance is directly proportional to the frequency and capacitive reactance is inversely proportional to frequency. XL directly proportional to F and XC directly proportional to 1 by F. Resonance curve of series RLC circuit. This is the figure of resonant curve of series RLC circuit. From here we can understand that at below resonant frequency XL is low and XC is high. The circuit behaves like capacitive circuit, that is leading power factor. At a resonant frequency XL and XC are equal. Circuit behaves like a purely resistive circuit, that is unity power factor. At above resonance frequency, XL is high and XC is low. Circuit behaves like a inductive circuit, that is lagging power factor. Note, in a series RLC circuit, the impedance Z equal to root of R square plus XL minus XC whole square. At resonance, the magnitude of inductive reactance is equal to capacitive reactance. At this condition, Z equal to R. Hence, at a resonance, the impedance is purely resistive and it is minimum. As impedance is minimum, the current is maximum. As impedance is purely resistive, the power factor is unity. Question number 40. The time taken for a surge to travel 600 km long overhead transmission line is typically, answer is option D, 0.002 second. Given length of the transmission line L equal to 600 km, we know the velocity of the wave V equal to 3 into 10 raised to 8 meter per second. It's the time taken. The time taken to travel for a surge T equal to L by V. Substitute the value of L and V, we get T equal to 0.002 second. Question number 50. The maximum torque of a three-phase induction motor running condition is, answer is option B, inversely proportional to rotor reactance at a standstill. From the diagram, we can observe that the maximum torque of an induction motor is independent of rotor resistance, but slip at which maximum torque occurs depends on rotor resistance and they change on adding the additional resistance to the rotor circuit. The maximum torque of an induction motor Tmax equal to Ke20 square divided by 2 x20. Therefore, maximum torque is directly proportional to supply voltage and maximum torque is inversely proportional to rotor reactance. Hence, the maximum torque is dependent on the supply voltage and reactance of rotor and is independent of the rotor resistance Sm. The value of slip corresponding to the maximum torque is Sm equal to R2 divided by x20. Therefore, slip at which maximum torque occurs is directly proportional to rotor resistance R2. Question number 16. In a moving coil instrument, the damping torque is developed by, answer is option B, eddy current. The deflecting torque is used for deflection. The controlling torque acts opposite to the deflecting torque. So before coming to rest, the pointer always oscillates due to inertia. So to bring the pointer rest within a short time, by reducing oscillation, we use damping torque without affecting controlling torque or inertia. The following mechanism can be used for producing damping torque. First one, air friction damping. Second one, fluid friction damping. Third one, eddy current damping. The damping device should be such that it produces a damping torque only while the moving system is in motion. To be effective, the damping torque should be proportional to the velocity of the moving current but independent of the operating current. In the moving coil instrument or PMMC type instruments, damping is provided by eddy current damping. Eddy current damping. When a conductor moves in a magnetic field, an EMF is induced in it. And if a closed path is provided, a current known as eddy current flows. This current interacts with the magnetic field to produce an electromagnetic torque which opposes the motion. This torque is proportional to the strength of the magnetic field and the current produced. There are two common forms of eddy current damping devices. First one, a metal former which carries the working coil of the instrument. A thin aluminium disc attached to the moving system of the instrument. This disc moves in the field of a permanent magnet. A disc should be of conducting and non-magnetic material. Type of damping and instruments used. Air friction damping, moving iron and electrodynamometer instruments. Fluid friction damping, electrostatic voltmeter ESV. Eddy current damping, PMMC and induction type instruments. Electromagnet damping, fluxometer. Question number 17. A house has 4 kilowatt connected load and is fed by single phase supply. What range of meter is connected for the house? In India, answer is option C, 30 ampere. In India, standard single phase supply voltage is 230 volt and it is not 7, and domestic power factor ranges from 0.6 to 0.9. Active power in kilowatt is P equal to VI cos phi, where cos phi is the power factor. For a 4 kilowatt single phase load, range of energy meter. Substitute the values, we get 4 equal to 230 I 0.6 into 10 raised to minus 3. After rearranging, we get I equal to 4 divided by 230 into 0.6 into 10 raised to minus 3. We get I equal to 28.98 ampere, approximately 30 ampere. Question number 18. The range of 1 milliampere meter is to be changed to 10 milliampere. The moving coil of the meter has a resistance of 36 ohm. What is the value of resistance to be connected in parallel? Answer is option B, 4 ohm. Given internal resistance of coil Rm equal to 36 ohm, total current I equal to 10 ampere, full scale deflection current Im equal to 1 ampere. Therefore, shunt resistance RSH equal to Rm divided by I by Im minus 1. Substituting the values, we get shunt resistance RSH equal to 4 ohm. Question number 19. In a 4-pole 25 kilowatt 200 volt wave wound DC shunt generator, the current in each parallel path would be. Answer is option B, 62.5 ampere. Given power P equal to 25 kilowatt, voltage V equal to 200 volt, total current I equal to P by V. Substituting the values of P and V, we get the total current is 125 ampere. In a wave wound generator, number of parallel path equal to P equal to 2. The current in each parallel path equal to I by A, which is equal to 125 by 2, which is equal to 62.5 ampere. Question number 20. A 120 volt source has a series internal resistance of 1 ohm. The maximum power that can be delivered to a load is. Answer is option B, 3600 watt. The maximum power theorem for DC circuit states that when the load resistance RL equals the Thevenin equivalent resistance across RTH, then maximum power is transferred to the load, that is RL equal to RTH, then maximum power is transferred to the load. The maximum power transferred is given by P max equal to VTH square divided by 4 RTH. Given VTH equal to 120 volt and RTH equal to 1 ohm, the maximum power transferred to the load is P maximum equal to VTH square divided by 4 RTH. Substituting the values of VTH and RTH, we get P max equal to 3600 watt. Thank you.